So this is an example on 2D heat conduction problem. So all the domain, as you see, is broken up in 3 node triangular elements. So okay, so A, B, C, D, E, this edge is gamma 2 boundary or S2 boundary. So S2 and gamma 2 we are using for the same type of boundary. So it's the gamma 2 boundary, or you can call it S2 boundary. So here convective heat transfer is occurring at this boundary with this value of H, but H is different on AB and B, C, D, E. So these are the two values of H. And there is a generation term within the domain, so that is G, and this is this. So now for 2D heat conduction equation, you know this is the governing differential equation in omega. So in the standard equation which we studied for quasi-harmonic, as quasi-harmonic equation, this G is actually minus F, because we studied this plus this equal to F. So that means minus F. So minus F is G, or F equal to minus G. And here this is the convective boundary condition. So in this convective boundary condition, this is actually Q. So Q is minus HT infinity, and this is okay. So if you make these two small changes, then this becomes the standard quasi-harmonic equation. So now suppose we are trying to find out the element equations for the element A, B, C. So for this element, maybe it should be something like this. It should be something like this. It should be something like this. This is modeled as. There should be something like this. AB. So these are the coordinates in meters. So these are the coordinates in meters. A is this, B is this, C is this. We call them 1, 2, 3. And we know this is the shape function for 3 noded triangular elements, where A1, B1, C1 are this, and A2, B2, C2. Here I is equal to 1, 2, 3, N1, N2, N3. That means I is equal to 1, 2, 3. So there is A1, B1, C1, A2, B2, C2, A3, B3, C3. And these the suffixes, they actually change according to cyclic order. That means for A2, this should be x3 y1 minus x1 y3. B2 would be y3 minus y1, and C2 would be x1 minus x3. So this is the area of the triangle. So now this is the element stiffness matrix Ke. This is B transpose dB T dAe, where this is B. So now if you take these differentiations, if you differentiate this with respect to x and with respect to y, then you get Bi and Ci. So this is the B matrix, and Ke, you know, B transpose dB T dAe. We take the thickness to be 1 meter, that is unity. So this is the stiffness matrix. As it is not dependent on dAe, you can take it out of the integral. Only dAe will get integrated to the area of the triangle. So you multiply this matrix multiplication, and for our case kx is ky equal to k, that is isotropic, and k is also same all over the domain, so it's homogeneous. So this is homogeneous and isotropic. At one point kx equal to ky, this means it's isotropic, and this kx and ky which are equal, they are also same all over the domain, so this is homogeneous. So this is Ke. Now you put the values, you get this as your stiffness matrix. So if you know the value of K, you can find out the stiffness matrix. And now you have to find out the column vectors. The column vectors will come due to the generation term. So you remember Fn1, Fn2, Fn3. In place of that, Gn1, Gn2, Gn3, Tdae, and N1 DAE is triangle by 3. So this is G triangle by 3, 1, 1, 1, and G is this triangular area is this by 3, 1, 1, 1. So this is this. Now this is the edge, the Cauchy boundary condition edge is gamma 2, that is 1 2 plus 1 3. So for this element 1 2, for this element this 1 2 and 2 3, these are on the convective boundary or the Cauchy boundary. So but in at 1 2 the value of h is different from the value of h at 1 3. So you have to use two values of h. So at edge 1 2, at edge 1 2, see at edge 1 2 n3 is 0. So n1 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 n2 n1 n3, n2 n1 n2 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 n3, n3 n1 n3 n2 n3 n3. So if n3 is 0, this term becomes 0, this term becomes 0. Now if you integrate, so in place of n1, actually now n3 is 0, so n1 and n2, n1 is 1 here and 0 here, and n2 is 1 here and 0 here. So n1, if you take a variable s from this side, then n1 can be written as this, that means 1 minus s by, so n1 can be written as 1 minus s by L12, because it should be 1 here and 0 here, and n1 will be 0 at 3. So n1 is 1 here and 0 here. So on this edge n1 can be on edge 1 2, and similarly because this has to be 1 here and has to be 0 here, so it it decreases linearly from a value of 1 to 0. Then what other function can it be other than this? And n2 would be equal to s by L12, because n2 is 1 here and 0 here. S we are measuring from 1 and going towards 2. So and n3 is 0. So n1 is this square, n1 n2 is this, n2 n1 n2 n2. Now if you integrate, you get this value. Now you put the values of h12 and l12 and you get this matrix. For similarly for h23, l23, and n1 is 0, n1 is 0, n1 is 0 means this term 0, this term 0, this term 0, this term 0, and this 4 terms will remain. So these 4 terms are this. Again you have to put the values of h23, because h23 is different from h12. So these two are matrices. So please note for G you are getting a vector, for the generation term you are getting a vector, as for F you get a vector, but for this term, this HT term you are actually getting a matrix. So for HT term you are getting a matrix. Similarly H1 for HT infinity term you get a vector, as you get from Q. So on edge 1, 2, 3 is 0. So this is this and this half half. Put the values of H1, 2 and T infinity. And on H2, 3, N1 is 0. So these two is 0 remain. So again for that means please carefully note that for this term you get a vector, for this term you get a matrix, and for this term again you get a vector. So that's that. And now again a comparison at the end with the standard form. So this is the standard form equal to f, and this is the standard form with which we started. Now this standard form and for this standard form, this is the element stiffness matrix. This is coming from this term, the boundary term, and this R is coming from this and this. So here also actually plus G. So in place of minus F you get plus G, and this is plus G. So for that you are getting minus HT infinity. So since this F is minus G, for the first term you are getting this, and for this term you are getting this one. This again you are getting a vector, and for this you get a matrix which is same as, for this you are getting a matrix which is same as this, what you are getting here. So and here there are two terms you are getting. So here you are getting a single term for N1G, but you are getting two terms because one is on H12 and the other is on H23. So this is the example. Now you can solve this. If you know the value of K, you can solve this equation. You can solve this equation and get the values of temperature distribution. Okay, so let me stop here.